to make it anti-periplanar so it reacts? Okay. All right. So in context, when we do E2, when we do an E2 reaction, we want to make sure that the hydrogen is anti-periplanar. In a ring system, that means that the hydrogen, the beta hydrogen, has to be what? It has to be trans. So in an acyclic system, in a non-ring, what we have to do is we have to put the hydrogen in the anti-periplanar in the sawhorse projection or in the Newman projection. So for instance, if I had something like this, and let's say I was to react this with NH2 minus. So if I reacted this with an NH2 minus, then I would say, okay, good. You brought me every white piece from my part.
Just wanted to make sure.
That's fine. Okay, thanks.
You bet.
So if we do the elevator's broken on the other side. I'm not going to fix it till 9. I can start fixing it at 8 o'clock this morning. I'm going to have a very nasty conversation with somebody soon. Okay. So if I gave you this reaction and said, what's the major product of the reaction? The first thing that we should do is what? Hannah? Okay. So we start with alpha and beta carbons, and then we determine which of the beta hydrogens can be removed. In an acyclic system like this, all I have to do is rotate around the bonds and put the hydrogens in the anti-periplanar geometry. So they can be removed. In a ring, if it's cis to the leaving group, it can't be removed. So identify your alpha beta carbons and then look at the potential beta carbon or beta hydrogens that can be removed. So in this case, we have this beta hydrogen and we have one of those 3 beta hydrogens, and they can all be removed. So we then say, okay, NH2 minus is going to produce what kind of product? The most stable, the most substituted product. So that means of beta hydrogen A and beta hydrogen B, which hydrogen is it going to remove? Melanie? A? We agreed that A would be the one that's removed? Okay. So that means I'm going to remove A, but right now, A is not anti-periplanar to the chlorine. And we need to make it that way because the product is either going to have the methyl groups cis or the methyl groups trans. And only one of those 2 possible stereochemistries is going to form. So what do I need to do? I need to put the hydrogen into the anti-position compared to the chlorine. A couple ways I could do that. I could just say, you know what, I'm going to rotate the hydrogen down a little bit, and I'm going to put it in the plane. So over here, the chlorine, the hydrogen, and the methyl group on this side, nothing's going to change. But if I move the hydrogen now to the down position, the hydrogen was towards you, so I'm going to move it so that it's in the plane. And that means that this group is going to come forward, and the CH3 group is probably going to go, well, the CH3 group is still going to be in the back, because I'm making a 30-degree rotation. So that means that, if you remember, they look like this. The CH2, CH3 group is going to be forward because it was in the plane, it's coming towards you. And then the CH3 group, even though it's rotating, it's still going to be placed behind you. If you don't like that approach, then recognize that the original molecule here, if I come over here and I take a look down the carbon-carbon bond, is that staggered or is it eclipsed? Eclipsed. So if it's eclipsed, that means that it's going to start like this. The front carbon has the ethyl group here, the hydrogen here, the methyl group here. The back carbon has the chlorine here, the methyl group, and then the hydrogen is away from you. And now what I need to do is now I need to rotate that front carbon so that it looks like this. The hydrogen comes here, then the methyl group goes there, the ethyl group goes there, the chlorine is here, and the methyl group is here, and the hydrogens there. Nothing changed on the back carbon, it only changed on the front carbon. So now if I put it in that conformation, the base is going to come in, deprotonate the hydrogen, chlorine leaves. Same thing is true over here. NH2 minus comes in, grabs the hydrogen. And so the two bolds end up cis, which is the ethyl group, and the methyl group end up cis, and then the methyl group and the hydrogen on the dashed end up cis. So this would be the only product of the reaction. The other stereoisomer, I guess this one is Z. The E isomer would not be formed. So so in an acyclic system, we have no choice but to put the beta hydrogen in the anti-position compared to the leaving group. And so notice that the reason I asked you this particular problem is because if I did this reaction with tertiary butoxide would be going after beta carbon B. And so I wouldn't make you do the rotation to get the beta hydrogen into the anti-periplanar geometry. But only this product is formed. So if you had the E, you'd get half credit. Okay. And I think there were a lot of these in the book that they had you do. But the steps are still the same. Identify alpha and beta carbons, identify the beta hydrogens that can be removed, and then put the beta hydrogen into the anti-periplanar anti-position so that it can be removed, so that you get the right stereochemistry. In the Newman projection, the groups on this side are going to be cis, and the groups on this side are going to be cis. So it's just like the two bolds become cis and the two dashes become cis. Does that make sense? What else? If it was tertiary butoxide, let me see if I can just rewrite it. So if I said, react this, give me the major product with tertiary butoxide, then you would still do the same thing. You would say, okay, here's my alpha carbon, here's my beta carbon, here's my other beta carbon, except methyl and ethyl don't work well when you're identifying carbons. So there's my two beta carbons, and so can each become anti-periplanar? The answer is yes, they both could become anti-periplanar. And so now we go to the tertiary butoxide and we say, which one is it going to preferentially remove? And the tertiary butoxide is going to remove the hydrogen that is most, not sterically hindered, but most accessible. I should have said least. So least sterically hindered or the most accessible. When I look at those two hydrogens, I see that this hydrogen is a tertiary hydrogen, whereas the CH3s are primary hydrogens. And so that means the tertiary butoxide is going to go after the primary hydrogen. And so if I just write this as a CH2 with the H there, the tertiary butoxide is going to grab that hydrogen, the pair of electrons is going to move there, and the chlorine is going to get kicked off. Okay. Which means that the left-hand stereochemistry, nothing changes. So I can just rewrite that. And over here, I'll have a double bond to the CH2 with the H. So that would be the major product if tertiary butoxide was used, and the other product would be the one if NH2- was used. So sometimes the problem is that with these ones, there's always going to be a way to remove the beta hydrogens because there's free rotation. In the rings, there's not always that. So the problem in the ring is that sometimes you only have one hydrogen that can be removed. That's it. That's going to be removed by NH2-. It's also going to be removed by tertiary butoxide. So you've got to put that extra step in to determine, okay, which hydrogens can be removed, because if a hydrogen can't be removed, that product's not going to form. So I could very easily give you this same molecule and say, give me the major product with NH2-, give me the major product with tertiary butoxide. And I'm pretty sure I've probably done that on one of the older exams. What else?
Giving a reaction that's either SM1, SM2, E1, or E2, or like the steps.
Okay, so let's say I gave you So let's just start with this molecule. What kind of nucleophiles can I add to this? Let's say I add water, could be one reaction. Hydroxide could be a second one. NH2 minus could be a third one. And tertiary butoxide could be a fourth one. Well, that's good. That's one molecule, four problems. That's pretty efficient. So, how am I going to determine what reaction, what the mechanism for each one of these reagents is? So, give me your choice of the four reactions.
H2O.
Okay, what is it?
It's a weak nucleophile.
Okay, it's a weak nucleophile plus what kind of halide? Primary, secondary, tertiary. Secondary. So we can use a chart. We have to go back and we have to remember the chart. So when you said water was a weak nucleophile, that automatically made it a one mechanism. So one mechanism, SN1 and E1. So with water, you would write the SN1 and the major E1 product. And that's from the chart. Secondary halide plus weak nucleophile, automatically SN1, and we added SN1 and E1 a while back. So we modified our chart from last time. What would happen with hydroxide then? Now I've got secondary halide plus what kind of nucleophile? Strong, so that mechanism would be SN2. So the hydroxide would be an SN2 mechanism. And then the NH2 minus and the tertiary butoxide.
So on the chart, it's just E1 and SN1, not SN2 and E2. Like it's
Right. SN2 and E2. So SN1 and E1 share the same first step, right? Yeah, that's a question that people have asked. So SN1 and E1 go together. And the reason that they go together is because the first step of the mechanism is the same. You break the carbon-chlorine bond to make the carbocation. And then the question is, do you lose a beta hydrogen to get the double bond, or does the nucleophile add to the carbocation? So that's why they're linked together. But SN2 and E2 are totally separate. There's nothing, right at the moment, there's nothing connecting the two of them. Okay. And the reason for that is, in the book may kind of have linked them together a little bit, because the question is, if I've got a strong nucleophile, that's also a strong base. So when I'm reacting with strong nucleophile, strong base, the question is, what's the nucleophile going to do? Is it going to act as a nucleophile, or is it going to act as a base? We've eliminated that question by saying these are the only two bases that we're going to use. And so we're just going to say, whenever you see that, it's E2. Whenever you see NH2 minus, it's E2. Because what they used things like CH3, CH2O minus, and I'm kind of avoiding those right now because that's a strong nucleophile and a strong base, and so what's it going to do? And without confusing, what I've said before is that when you have something that has this, like, I don't know, it's got this bipolar type behavior, It can do either one. So the first thing it tries to do is be a nucleophile. And if it's like rebuffed, meaning that the halide is like tertiary, it would try and do an SN2, but the tertiaries don't do SN2, so then it would go back and it would deprotonate. But we're going to ignore those and just say our E2 mechanisms are always these guys. So the books kind of introduced that complexity, which I'm going to hold off on until next semester. And then we'll go into the gray area of that. Okay. So these two guys are always E2. So that's how you would determine the mechanism. Use the chart. But then the chart would have a column. So if we had our chart of primary, secondary, tertiary, and then we had our strong nucleophile, our weak nucleophile, then we would have NH2 minus and tertiary butoxide in the column, in a third column, and these would all be E2, E2, E2. So they would automatically create an E2 mechanism. So that's how you're going to determine whether the reaction is SN1 and E1. And whenever I ask for an SN1 and E1, you're always going to write the major product of the E1 mechanism. And what's the major product of the E1 mechanism? It's always the alkene that is most stable, most substituted. So for the SN1 and E1, there's actually going to be 4 products of this reaction. So if we think about the E1, if I again identify my alpha, beta, beta carbons, and then here's my 2 beta hydrogens. When we go to E1, does stereochemistry matter? No. Stereochemistry doesn't matter. So it doesn't matter in this case that the hydrogen is cis or trans. Because once you form the carbocation, either one can be removed. So in this case, if E1 gives me the most stable, most substituted product, then I'm going to get both alkenes. I'm going to get both of those products. As far as the E1 goes, those are both major products because, again, E1 gives you the most stable, most substituted double bond. Now, what about the SN1 part? Well, for the SN1 part, I'm going to get so I'm going to have my methyl group. Nothing happens between my methyl and my ethyl group, but I'm going to have the OH on the bold arrow, and I'm going to have the OH on the dashed arrow. I'm starting with a chiral alkyl halide, and whenever you start with a chiral alkyl halide and you do SN1, what do you end up with? A racemic mixture. So in this case, the racemic mixture is going to have the bold, the OH bold, and the OH dashed. So in other words, when the chlorine's lost in the carbocations form, the water is going to add from the top 50%, water is going to add from the bottom 50%, and so it's going to be on the bold and the dashed. So for that reaction, there are 4 products. And as strong as the temptation is to make those kinds of questions multiple choice, you're going to have to write the products out. Now, if you're like, well, okay, so the statistics are, if I give partial credit, which I always do, you could at least get some of the 4 versus none of the 4. So the statistics are on your side for that one. So, but that's the way you want to approach it. You want to say, okay, E1, same steps, identify alpha beta carbons, and then which is the most stable products, write those down, and then when you have SN1, okay, where's the OH going to go when it starts chiral? And in this case, it's a racemic mixture, so it's going to be both bold and dashed. For SN2, what's going to happen, though? So for SN2, the first thing I would think about is I would say, okay, I'm going to substitute the chlorine with an OH. So nothing else in the molecule changes. Nothing happens to methyls, nothing happens to the ethyl group. The only thing is I've got to put an OH in here. Bold, dash, 50-50. For the SN2. Katie? Dashed? We agree? I mean, I can easily erase. Why is it dashed? So SN2 goes by inversion of configuration. And remember, inversion of configuration just means that I switch 2 groups. So instead of there's always a hydrogen here. So I'm going to switch the position of the OH and the hydrogen. If you don't like that, okay, the chlorine's pointed above the ring. How's the OH going to add? It's going to have to add opposite, right, underneath. And so that's going to leave the OH with a dashed wedge. So that would be the only product of SN2. And then for the NH2 minus and tertiary butoxide, we go through the same steps. Identify alpha and beta carbons and identify which beta hydrogens can be removed. So in this case, if I have HA and HB, so if I label these HA and HB, which one is going to be which one can be removed by either of the bases? A, B, or both? Either of those 2 bases are doing E2, so what does the hydrogen have to be? Antiperiplanar, which in a ring system means that it has to be trans. And so which one of those 2 is trans? B. So when I do those E2 reactions, only the B hydrogen can be removed. And so that would lead to this product over here. That's going to be the product of whether I use tertiary butoxide or NH2 minus. That's going to be my major product. Okay. So we have to slip that extra step in of determining which hydrogens can be removed, because if only one hydrogen can be removed, I don't have to worry about, well, which one is less sterically hindered. It doesn't matter because only one hydrogen can be removed. If more than one can be removed, then I have to go to, okay, tertiary butoxide is going to remove the less sterically hindered, etc. You'll probably find one of those kinds of problems on an older exam as well. I mean, I think it's a good one. So
can you not rotate the hydrogens in the cyclohexane like you can for the
no. You can't rotate. I can't bring that hydrogen, the one that's on the dash, or the one that's on the bold, I can never make it behind or make it on a dash wedge. If I do, then what happens is the chlorine is never anti-periplanar. Because the only way in a ring, the only way in a cyclohexane ring is to have the chlorine axial and then have the beta hydrogen axial. And so that means that they have to be trans. If they're cis, I can never twist the ring enough to make them anti-periplanar. So that's what makes that easier.
So then if there's only the one beta hydrogen that can be removed, how do you know then which of the, like if it's tertiary butoxide or NH2?
You're going to get the same product.
Oh, okay.
If you can only remove one beta hydrogen, there's only one product.
Okay.
And so it doesn't matter what base you use. If more than one can be removed, then it might matter. It's this one. It's going to be that one. It's going to be the one that I wrote over here in red. So that's going to be the same product for both reactions with the double bond down. Maddie?
For the hydrogenation and the hydrofluoration, do you not have to know how to write the hydrogen?
No.
You just know like
Just how to write the products. So if I said, so all I can do for that one is do this. What's the major product of that reaction? What's the major product of that reaction? Well, and is the reaction regio, stereo, both, or neither? So that's where in terms of writing the products, if you've noticed, I've kind of done it this way for each, where I've put in the groups, but I haven't put in the types of bonds. So for BH3H2O2, the first thing I need to know is what am I adding? What two groups am I adding? H and OH. Are they adding Markovnikov or anti-Markovnikov? Anti. So that means the hydrogen is going to be added to the top or bottom carbon. it's the opposite of Markovnikov. So Markovnikov would be what? Adding the H to the carbon with the most hydrogens. In this case, I'm going to add the hydrogen to the carbon with the least hydrogens. So that means the H is going to go here and the OH is going to go there. Right? That's anti-Markovnikov addition. Okay. Stereochemistry. H and OH are added what? 100% cis, 100% trans, 50-50. %, cis, so that means they both get the same bond. Whether it's bold or dash, they both get the same one. So then that would be my major product of the reaction. For the second one, same kind of process. What am I adding with H2? I'm adding two H's, right? So I'm adding two H's. Markovnikov, anti-Markovnikov. Doesn't matter, it's the same thing. So that means I'm adding two H's. Cis, trans, 50-50. Cis. So again, they get the same wedge. They get the same wedge regardless of whether it's bold or dashed. So then that would be the major product of the reaction. Maddie?
So like to determine like if it's regioselective versus stereo, would you recommend us to just remember like this flow chart?
Well, I put the flow chart together to kind of maybe organize it. So there are certain things that we can remember that will eliminate the possibility of it being one or the other. And that's kind of on those flow charts. And I don't know, you could make the flow chart 100 different ways. Well, probably more like 5, but you could put them together differently. So so if we started with the idea of regioselectivity, the first two questions that you ask, remember, I've said at least a dozen times or so that if either reagent is symmetrical, the alkene or the reagent, once it's symmetrical, regioselectivity is over. There's no regioselectivity. So, and that's what all those questions are. Is the alkene symmetric? If the answer is yes, you're done. Is the reagent symmetrical? If the answer is yes, you're done. No, it's not regioselective. And then it really boils down to, okay, when will the reaction be regioselective? Well, number one, when the reagents are asymmetrical. And then when you add both groups to the double bond this way, and you get two different products, it could be regioselective. And it will be regioselective if you add the hydrogens this way, or if you add the groups this way, and you get two different products, and one of those is the major product. And to be honest with you, that's where the Markovnikov, anti-Markovnikov comes into play. So if and I put together the chart, which you could have put together as well, and I would encourage you to maybe put one together in whatever system you use. Anytime there's like neither, that's never going to be regioselective. So if we went to that, let's see. The one thing I do not like about Canvas is when I go backwards, it always goes back to the beginning. It just should go back to where I was before. But so if we look at the chart here, and like I said, this is just my chart. Anytime it says neither, those reactions are automatically going to be not regioselective. Now, any of the other ones with a symmetrical alkene, not regioselective as well. And the reason I put the intermediates in here was for a couple of reasons, because number one, if you have a carbocation intermediate, what does that eliminate? Stereoselectivity. So anytime there's a carbocation, you can't have stereoselectivity. The triangle means that you're always adding 100% trans. Triangle trans, I guess, if you're into that. Square means cis. So that's the reason why I put that there, is to kind of maybe give you something to remember. Because you don't have to do the mechanisms of the last two. But if you get stuck, it's like, what does the hydrogen do? And then if you kind of think about it, okay, palladium. So the hydrogen is going to stick to the surface, and then they have to add cis. Or the boron, hydrogen, that's going to be another. I mean, we only have triangles and squares. Next week we'll have a pentagon, which is still cis, by the way. So we'll have those. Only the triangle is trans. So that's why I kind of organized it that way. But you know, one of these days when I need additional salary, I'll put together like flashcards with all this stuff on it and sell it to people. But then again, you're already purchasing this already with your tuition. So, but honestly, you have to organize this in your head your own way. So this is just my suggestion. So that flow chart is nothing more than trying to say, okay, the big rules that I've kind of given you, it's just kind of organizing them in a way that may make sense. And honestly, the more problems that you did using that, you're going to learn it, right? So looking at that, like, so for the stereoselectivity one, does the reaction undergo have a carbocation intermediate? If the answer is yes, then it's automatically going to be 50-50, and there's going to be no selectivity. Does the reaction then go 100% cis or trans? If the answer is yes, it could be, but we haven't confirmed that yet. So then what do? You do the same thing. Add the two groups cis, add the two groups trans, and then we can cut right to the chase. Did you form two chiral centers? When you did the first one, did you form two chiral centers? And if you did, and the reaction's 100% cis or 100% trans, it's going to be stereoselective automatically. But otherwise, atom cis, atom trans, the option is both of those would be diastereomers. If you selected one, and how do you select one? Make the reaction 100% cis or 100% trans. So the flow chart just kind of, I don't know. It just kind of reinforces that. It just takes all those things together and puts them. So there's probably people who would be like, they should do this on their own. I agree. But make this your own. Think about that in terms of what is it? What do the steps mean? So yeah, you could. Would I say memorize these charts? I guess if that's like hitting an ant with a hammer. But if it works, it works. But if you think about the steps, again, for regioselectivity, adding them this way and this way has to produce two different products, and you've got to select one. and that's by Markovnikov or anti-Markovnikov. If you add them cis and trans, you need to produce two different products, which means two chiral centers, and you got to select one. That's what it all boils down to. And unlike the older exams where I've sort of summarized that in the end, because then it makes it easier for me to grade, I will probably ask you reaction by reaction. Is it regio, stereo, both, or neither? Okay. But remember that if it's symmetric, if I start with a symmetrical alkene, it's not regio. So I thought I had placed some problems on there with the different cyclohexanes, and I did put those in. Those are in this folder as well. So that if I start with cyclohexene, I get one answer. I put a methyl group, I could get a different answer. I put two methyl groups, I can get a third answer. And if I put a methyl ethyl group, I could get a fourth answer. So this is really about each and every reaction has to be taken individually. But there are some big rules. BR2 will never be regioselective. So that's where I would say, you could, if this helps, then just remember those, try and remember those steps. And remember the big things that automatically eliminate it. Anything else? All right, if anything else comes up, you can stop by, send me an email. Like I said, the older exams, the reactions on the older exams that will not be part of this test is anything with mercury. And anything you see with a three-membered ring with an O in it, that's an epoxide. We haven't done epoxides yet, and we haven't done mercury. So all the other reactions should be fair game. But if you have any questions, email me or come see me. And otherwise, I'll see you on Friday.